Hi, and welcome to my third video on cutting of 4140 chromoly steel in its annealed, heat-treated, and tempered states. And the reason for this third video is, in my first two videos, I was discussing how the material turns on the lathe, because that's what I was doing when I was using it, and I was having terrible troubles getting a good finish. The thing is, on a lathe, your cuts are continuous, provided the material's round and doesn't have holes in it or anything. But for round material, it's uninterrupted cuts. If you're cutting longitudinally, the cut will be essentially a very tight spiral around the part. When you're facing, it'll be a very tight spiral around the face, usually from the outside to the inside. So what I wanted to cover also was some milling cutting, and this can be a fairly brief video, and see how the material performs when you're dealing with an interrupted cut. Because when you're on a milling machine, whether you're facing a part like here or you're dimensioning a part as shown here, in both cases they're interrupted cut. As the cutter comes around and engages the part, it's deflected slightly in the direction opposite of where it's cutting, and finishes the cut, and then the force is gone and the part springs back a little bit. So in this case that I'm showing here, as the tool engages the part right at the end, there's a force in this direction, and that is going to deflect even carbide parts ever so slightly. Similar down here, when you're doing a dimensioning cut along a side, there is going to be a force away from the part as each cutter tooth engages the part. The deflection is minute, but surface finish is affected by minute changes in cutter position. So even if your machine is perfectly stiff, which not all of us have, really big, beefy, heavy machines, machine deflection will play into that. Even without that, the cutter itself will deflect. High-speed steel more than carbide, which is twice as stiff, and I think it's worth investigating just to see what happens. So we're going to take a quick look and check this out. So before we get over to the mill, I wanted to bring up something one of my viewers had mentioned in discussion, and that's speeds and feeds. And it's a very important topic, and it can help improve your surface finish, and it can also save your tools, and that's probably the biggest key, especially for the home hobbyist, because tooling is really expensive, and blowing out a tool is probably an expensive fix. So Niagara Cutter provides this chart here, which helps give you a general idea about how to set your speeds and feeds. Now, it's for their specific cutters. In this case, they have a high-speed steel with PVD coating and a solid carbide with PVD coating chart. You might have to adapt it slightly for your own uses. This used to be available for free on their website. I got it at the Summer Bash. I don't know if it still is, but you can check that out. Niagara Cutter makes some great cutters. My very first experience with machining, I used a bunch of really crappy cutters, and finally got a Niagara Cutter, and it was night and day, so it really had a strong impression on me. So the way this chart works on one side is you pick your alloy. For example, here is medium alloy steel, which includes 4140 for a high-speed steel cutter, and you come down here and it's 50 to 200 surface feet per minute. 5/10 thousandths to 5 thousandths inches per tooth, a feed rate. For carbide cutters, you just slide down to the bottom section and go back to 4140 and 200 to 500 surface feet per minute with the exact same feed rate, between half a 10,000th and 5 thousandths inches per tooth. Now, that's based on the diameter of your cutter, so that's cutters varying between 1/8 of an inch to 1 inch in diameter, which is what they cover here. So if you knew your cutter size, say if we had a cutter diameter of 1/2 inch, which reading off the chart means it's 2.5 thousandths inches per tooth, to convert that to inches per revolution, we just use a conversion factor, and I'll explain a little bit more about that in a minute. So 2.5 thousandths inches per tooth times 4 teeth per revolution. If you notice, the tooth and tooth, they cancel out, which leaves you with 10 thousandths of an inch per revolution. And the real beauty of doing math like this is that when your units cancel, and you should always carry your units along with you without doing proper English grammar, changing tooth to teeth and whatnot. When you're done, whatever you're left with is what your units will be, and that's the advantage of conversion factors. On the back side, if anyone's trying to figure it out, it helps you convert surface feet per minute, which is what their cutter speed is rated at, to RPMs, which is really handy on the top. And then they've also got feed per tooth chip load, and stock removal amount, and hardness conversion, just a general hardness conversion chart. So for a 1/2 inch diameter tool, since you won't be able to read this on camera, 50 to 200 surface feet per minute for a 1/2 inch tool equates to 400 to 1500 RPM. And 200 to 500 surface feet per minute equates to 3000 to 4000 RPM for a 1/2 inch tool, which is really fast for a home milling machine. However, they qualify all of these for HRC materials 32 and lower. So the annealed material is certainly below that. It's around 13. The hardened and tempered part is actually Rockwell 39 approximately. And the heat treated only part is Rockwell hardness 54 to 59. So as your hardness increases, your surface feet per minute need to go down accordingly. And if you don't, you will damage your cutters and have to buy new ones. So I think we should be careful as we proceed, and we will use these as guidelines and kind of deal with that appropriately. I looked up on one site, and basically doubling of hardness means halving of surface feet per minute as a very approximate approach to this. So that would mean between the annealed part and the tempered part, heat treated and tempered part, should have about half the surface feet per minute, which, if you notice the range here, that fits within that range, and this is sort of at the top end of that. So 50 might be appropriate for a 1/2 inch tool for high-speed steel, or 200 might be appropriate for carbide. The heat-treated material, going to have to handle with kid gloves, so I will start really slow and work up for that one. Alright, so I thought I'd help some of you out. For those of you that know this already, please just skip right by it. But, you know, we're not all great at math, so I thought I'd help take some of the mystery. And there's a little trick you can use when you're trying to convert units to make sure that you end up with the right result. So if we start with a 1/2 inch diameter tool, diameter being the width of the part, width of all the way across the round part, the radius would be half that, and the circumference would be the length around the outside of that part. So if you have a 1/2 inch diameter tool and you need to know circumference, because when a cutter is cutting, every time it rotates, the cutter covers that much distance. So that's one of the key values we'll use below. So for circumference, it's pi times the diameter, or twice the radius times pi, which makes perfect sense, right? So if I have a 1/2 inch part and pi is 3.1415, that means that the circumference, which I didn't write here, sorry. Circumference equals 1/2 times 3.1415, which will equal, there's only one unit in here, this is a unitless value, 1.5708 inches. So that's the circumference. So that's the length around the outside of the round part. Now, if I wanted to convert that to feet, since we're looking for things like surface feet per minute, there's actually a trick. When you use a conversion factor, everyone knows there's 12 inches to 1 foot, or for the metric people, 100 centimeters per meter, etc. Those conversion factors are essentially 1 divided by 1. They're a unity thing, so you can flip them over. 1 foot per 12 inches is just as true as 12 inches is in 1 foot. So when I want to convert inches to feet, I orient this conversion factor, 1 feet per 12 inches, so that the inches are on the bottom, so that they will cancel out my inches that I start with. So if I start with 1.508 inches, and I have 1 foot every 12 inches, the English part doesn't really work with the math, but the inch part cancels out. Just like any other in a fraction, you know, if I had 2 over 2, I can cancel that out and leave 1. Inch over inch is 1, I can cancel that out. That leaves me with 1.508 divided by 12 feet, which is 0.1309 feet. At the end, I know I have the right answer, because the only units left are the units I'm interested in, and provided my conversion factors are correct, then I will end up with the right result. If this had been backwards, 12 inches over 1 feet, I would have 1.508 times inches times 12 inches, which would leave me inches squared divided by feet. Makes no sense, right? So if you know the conversion factors, which are very easy to find, you can convert between anything and anything, that, you know, any unit, any like value to another like value. So the next step to find RPMs from this would be, if I knew that I needed 50 surface feet per minute, and I'm going to throw the surface away because that's just a descriptor, 50 surface feet per minute, I'd multiply that by 1 revolution per 0.1309 feet, which is what I calculated here. Because this part is round, the circumference is 0.1309 feet, so every time it goes around, we cover 0.1309 feet. Now, I could put this either way. It's equally accurate to say 0.1309 feet per revolution, but I want to cancel out feet and end up with revolutions per minute. So 50 feet per minute times 1 revolution per 0.1309 feet, the feet cancel, leaving me 382 approximately revolutions per minute. So I have just converted my 50 surface feet per minute value that I got off this table, you know, the Niagara table. I've converted that with the diameter of my cutter without using their chart. Now, their chart is a really handy shortcut, so you don't have to go through these calculations. But in the future, when you want to convert between one thing and another, once you know the conversion factors, 1 foot per 12 inches, 4 quarts to a gallon, any of these things work. 1 gallon is equal to 4 quarts. 4 quarts is also equal to 1 gallon. That fraction works either way. Set it up so that the units will cancel that you don't want in your result, and whatever you're left with will be the right answer. Okay, let's actually go to the practical side. All right, so we're going to take our first test here on the annealed piece, the softest piece, and we're going to go at the low end of the RPM they recommended, so about 1500 RPM. And this is a single flute indexable carbide end mill. Let's see if you can see that there. I chose this because since I was going to push some things, I really didn't want to risk breaking one of my few 6 flute solid carbide 1/2-inch cutters. So we're going to give this a shot here and see how it goes. Call that 0, and I think we'll do a 25 thousandths pass. That finish is okay. definitely some scratches in there. Probably there's a single flute, so it's not going to be optimized for great finish, but it does cut easily. Let's head up to higher RPM, see what we get. So here's about 2,800 RPM, and I think I'll shoot for another 25 thousandths. There's 50,000 cut. So, once again, it looks like higher RPMs yield better finish with this material, single flute cutter. That's actually a pretty reasonable finish. I don't know, let me see if I can pick you up and get you a little closer here. So here's the finish at the higher RPMs. Alright, so here's going to be our first pass with the tempered stock. And I'm going to start around 1500 RPM. And since this is right at the limit of what that chart was saying for typical multi-flute carbide cutter, and I don't know that that really applies here, but we're gonna test this out and see what kind of finish we get. 25 thousandths depth of cut, same feed rate. Okay, so that's already better than the other stock. Let's see if I can get you a close up here. So we're gonna go full. All right, next pass, we're gonna try higher RPM. We're going to try about 2,800 RPM, see how that works. Sorry about that, I didn't really have you zoomed in, I left you wide. My bad. But again, the finish is improved, and I think the finish is even better on this tempered stock, the hardened tempered, than the annealed stock, and you can see it side by side here. I'll try and get you a better shot when we're done. Alright, we're going to move on to the heat-treated stock next. I'm trying to make this fairly simple and quick. So here's the heat-treated stock at 1500 RPMs. You can hear it struggle with the harder material. This is also about a 25 thousandths depth of cut with a pretty slow feed rate. The finish is pretty good. And now let's go to the higher RPM. and another 25 thousandths depth of cut. Now we're at 50. This finish is pretty amazing. Here, let's see if I can show you. So this finish is pretty amazing. Even when it hit the 50,000th depth of cut, didn't have much trouble with it. You can tell there's a little bit of tool deflection on one side as it is smooth going through, and then a little bit of rough on the trailing edge there. And there's compared to the tempered stock, as well as, let's see if I can hold them all together here, as well as the annealed. And again, harder material makes a better finish. It's a lot more difficult on the milling machine, the harder material. You can hear the squealing. One thing I could do to improve that would probably be to stick the milling cutter even deeper into the collet so that there's less stick out, because there's a tremendous amount of force in the cutting action there. So I hope this was useful. I thought it'd be interesting anyways, and just make a really short video just to cover what it's like with an interrupted cut milling. And the one takeaway is it's really loud. Oh, one more thing here. The cutter I was using was a single flute cutter, APKT insert, and it turns out I did have that all the way up to the top of the collet. So the only way to get less stick out would be to cut off the end of this so that I could get it deeper into the collet. But useful experiment anyways, and hopefully you found it interesting. Alright, so I made this really quick. I didn't really want to beat this whole topic to death. Typically, I could have used a whole bunch of different cutter styles, 2 flute, 6 flute, carbide, high-speed steel. But my goal here was not to investigate cutters, because typically more flutes on the cutter yields a better finish, and high-speed steel is not as hard as carbide, although sometimes maybe a little sharper. But on the harder materials, it probably wouldn't be a good idea unless you want a short tool life. So what I was really aiming at here was to investigate if the interrupted cut on a milling machine, you'd see a significant difference in finish between the annealed stock to the hardest just heat-treated stock. And yes, there is. The annealed stock, as usual, has little tiny tear-outs. It's still a better finish than I was typically getting on the lathe at low speeds, but there is a marked improvement as the material gets harder. However, the stress on the machine goes up, and you have to take that into account accordingly. So you'll have to take smaller depth of cut and that sort of thing, but less noticeable effect than the lathe. So that's my takeaway. I hope this was useful for you guys, and hope to see you next time.